Hello dear students, I hope you are doing fine. So let's have a new lecture on discrete mathematics. In the previous lectures, we learned about the foundation, logic and proofs, and also we learned about how to do programming in class, and also there were some lectures on this one. So in today's lecture, we will learn about propositional equivalences, which are very important to understand the topic. So three terminologies are defined here: tautology, contradiction, and contingency. So in propositional logic, if something is always true, we call it as tautology. So in order to understand the logical equivalences, we need to understand tautology. So the saying of the same thing twice in different words is considered as tautology. So for example, you say they arrive one after another in succession. One after another and succession, the same. In mathematical logic, a tautology is a formula or assertion that is true, always true, in every possible interpretation, no matter what the truth value of the propositional value that occurs in it. For example, x equals y, or x not equal y. So these two true. X can be equals to y or not equals to y. So this is considered as tautology. Or the ball is green or not green. So a ball has a color. It can be green or not green. These two together is green or is not green. These two together is considered as one tautology. So we say that a tautology is a statement that is always true. P or not P is always true. We call it as negation. So T, right? F, T. P, if P is T, P or not P is true, right? P or not P. P is true, not P is F. P or not P is true. P and not P is false. On the other side, we have a terminology of contradiction. Contradiction is a statement that is always false, right? P and here is or. This is and, right? P and not P is always false. P and not P. Here is or. Here is or. We can't say a ball is green and not green. And not green. It's false. It's a contradiction. Not acceptable. I can't say you are in the class and also you are not in the class. This is contradiction. But if I say you are either in the class or you are not in the class, this is a tautology and correct. And the last terminology is contingency, a compound proposition that neither tautology or contradiction is called as contingency. Logical equivalence, we use compound proposition that have the same truth values for all possible cases. We call that logical equivalences. Compound propositions that have the same truth values in all possible cases. A logical equivalences means that two sides always have the same truth, even though we change something, but still the same. So these are the symbols, these two are the symbols. And if we did this table, we can see the compound proposition P and Q. So here for and, we say that P and true. P and true is equal to P. So we added this terminology to one side, so we can say that P is always P, right? It doesn't matter if we say P and T, then it's also P, right? We call this one as identity law. P and F is always F. That's why we call it as domination law. P and P is always P in the law. P and Q equals to Q and P. This is called as commutative law. And P and Q and R, here we have three propositional variables. P and Q and R equals to P and Q. So it doesn't matter if we move the parentheses between these three, which is called as associative law. Let's see the truth table to better understand the concept. So here we have identity law and domination law. So let's see the truth table for these two. We say P and T is always equal to P. And here is n. So we go for truth table. How many possible variables, values for this variable we have? So this is called as variable. and these are called as values, possible values, you can say. So the possible values for variable p can be t or f, true or false. If it is t and the other side is t means always true. T and t, true and true, is always true. If false and true is always false. So you can see that these two sides are the same, right? Equal. That's why we call logical equivalence of n. For the determination law, p and f. So we go for variable p. The possible values for this variable, it can be either true or false. And for false, it's always false, right? True and false is always false. False and false is always false. That's why you can see that these two parts are the same. That is called as determination law. Here is the logical equivalence of and. For the idempotent law, so we say that p and p always equal to p, right? So we write the variable p, same value, t and t, f and f, okay? Commutative law says p and q equals to q and p. It doesn't matter when we change the position of the variables in and. You can see this is p, this is q. P and q, q and p. You can see these two are also the same. These two also the same. Using truth table, very easy to prove. But later we will see that if we have a long equations, using truth table is not possible. Here is the association law for the logical equivalence of and when we have three propositional variables, p, q, and r. So these are our variables, three variables, and here possible values for each variable, t, f, t, f, and ff. So here we want to prove the association law using truth table, right? So what we do, we go one by one from this side to this, right? We start from the left side ending with the right side, and we should see that these two parts are the same for this law. So p and q, do you remember there are some priority? So parentheses has priority. First we go for parentheses, p and q. So we will write p and q, true, f, true f, ft, f, and ff. Then we go for this column and r with this one, right? t, ft, f, tff, fff, tff, tff, okay. So this is one side we completed, right? This is one side. This is the left side. The right side, q and r, tff, tff, ftf, fff, ttt, tff, ftf, fff, okay? And then we go for p and qr. It means this column and p. So t and t, t and f, t and f, t and f, f and tf, tf and ff, f and ff, f and ff. So let's compare. Same. That's why this association. So using truth table, we prove the association law for L. Let's see the same thing for OR. P or T is always true. We call it as identity law. P or F is P, domination law. P or P is always P, idempotent law. P or P, Q is always Q or P. It doesn't matter if we change the position. We call it as commutative law. And if we have three variables, P or Q or R, it doesn't matter if we change the parentheses. We call it as association law. And here is the logical equivalences for negation or not. Not P is always equals to P. Not P is equal to P. We call it as double negation law. P or not P is true. Tautology, right? We call it as negation law. And also P or not P is false. And. P or not P is true. P and not P is false. This is contradiction, right? So this is tautology, this is a contradiction. We have a very famous law, which are two laws which are considered as De Morgan laws. De Morgan laws are probably the most important logical equivalences that we should know. De Morgan laws can be used in Boolean algebra, set theory, and also in propositional equivalences. So we have two, as you can see here, one is here and another one is here. In the first one, we can say that based on this De Morgan law, this is called as union and this is called as intersection. Based on this law, the complement of the union of the two propositional variables will be equal to the intersection of negation of both. In other words, if we apply negation to n, it will be changed to or. So not p will be not p. If we apply this one, the result will be this one. Not to n will result to or, and not to q will result to not p. So negation change and to or. The same here. Not p is not p, not a or will be and not q will be not q. Okay, that's all. These are called as De Morgan laws. The first one is called as De Morgan union law. The second one is considered as De Morgan intersection law. And in this table, this is the truth table in order to prove the De Morgan laws. So what we do? Let me remove. Okay, now I want to prove these two using truth table. So what do we have? We have only two, right? So 2, 1, p, and q. So these are the variables and these are the possible values. So what we do, not p, and not q. What we do, not p, it means tf, ft, and the same thing for q. Then we go for p and q, right? P and q. P and q is true, f, right? Then we go for right side, not p and q. This is p and q, we just not. T to f, f to t, f to t, f to t. Then we see the right side. So this is the left side, and let's see the right side. Right side says not p or q. This is not p, this is not q, right? Or f or f, f or t, t or f, t or t. Let's see, these two are the same. Yes, that's why using truth table we prove the union De Morgan law. And in order to prove that De Morgan intersection law, we do the same thing. P and Q, P or Q is here. So P or Q, true, false. Not P or Q, just you change it. T to F, T to F, T to F, F to T. And then you go for the right side. Not P and Q, this is. So you compare these two, whether the same or not. Yes, same, then it's proved. So those two De Morgan laws can be applied not only to two, but can be applied to a set of variables. Instead of having only two, we can say P1, P2, P3 up to something, and then not only one or two or many. And also, we can rewrite using this and or, like what we have for summation, right? You can use this one. So this big and from I to 1 to n pi. This is used for a set of, which is called as extended version of De Morgan law. And the same thing we can apply here. So this is and for a set, not for two. And this is or for a set of propositional variables. Let's see one example. So we want to show that P or Q and R and P or Q and P or R are logically equivalent. How we do it? Using the truth table. This is called as distributive law of this conjunction over conjunction. This equation is considered as distributive law of this conjunction over conjunction. And both are the same. First, we make the truth table for these compound propositions, right? So what we do the same. Here we have three variables, P, Q, and R. P, Q, and R. These are our variables, and these are our possible values for these three variables. So we do one by one based on the priorities. P and R. This is the first one. We do P and R. You know how to do it. Then we go for the second one, P or Q and R. This is Q or R. So this one we do it. P or Q and R. So this is one side. Other side is P or Q, this is the column. Q or P, this column. Then we compound them. P or Q and Q or R. Then we see these two, whether same or not. Yes, we simply prove. So using truth table, it's very easy. Just you need to know what is and, or, and not. Just you draw a table, you bring your variables, you bring the possible values for each variable, then you think about the priorities, parentheses, and or not something. Then you see both sides. You start from left side and go to the right side. Then you compare whether equal or not. If equal, it means you proved. So, for example, this is your assignment. Just here we did for this one, right? Then you'd go for the other side, right? This is the opposite side of the previous side. P and Q or R. Here you had P or Q and R. Here we have P and Q or R. Please prove it. Here we can see a set of useful logical equivalences for compound proposition involving conditional statements. Implication, right? P and P implies Q, P then Q equals to not P or Q. P implies Q, not Q implies not P. So when we end, the position changes. P or Q equals to not P implies Q. P and Q is negation of equals to negation of P implies not Q. When we have implication and we apply a negation to that one, the other side changes, right? P and not Q. And here, P then Q and P then R equals to P implies Q and R. P implies R, we have two statements, propositional logic, P and R, Q then R. If we end them, union them, then we have P or Q then R. And P implies Q or P implies R is logically equals to P implies Q or R. And if you have P implies R or Q implies R, it's equal to P and Q implies R. These are rules that we later use them. The previous slide showed one direction conditional statement. Then here we have bidirectional, right? So you remember by implication or by conditional statement. P and if only if Q, it means we can expand it. P and Q and Q and P, right? So this is logically equivalent. P and if only if Q is equal to if we negation to the same. We apply negation, it's the same. P and if and only if Q equals to P and Q or not P and not Q. And the negation of by implication is P if only if Q, right? So there are two ways for proving propositional equivalences. Proving using truth table and the logical equivalences. These are the two ways. The first one, prove using truth table, is extremely easy. As you already saw many examples we had so far, we can simply draw the tables, we can bring the variables and the possible values, just simply add based on the priority, we apply the operations, and finally we see the right and left side whether they are same or not. Very easy, but it doesn't work always because sometimes we have very long formulas and we cannot construct the truth table. The second method is logical equivalences. This is very good, but a little bit difficult. We need to remember the laws in order to prove something. So here, let's take truth table. We had many examples. So now we want to go for the logical equivalences to prove something, right? So we will try the second way for proving propositional equivalences by developing a series of logical equivalences. The second way is named as logical equivalences. So what is the example? We want to prove that this one equals to this one or not. Not P or not P and Q equals to not P and not Q, right? So this is what we have. We want to prove this one. So using the second De Morgan law, which was the law of intersection, we can rewrite this one. So look at here. We apply the not. So we start from here, right? We apply not to here. Not P is not P. This or will be changed to and, right? Then this whole, we have a not. So the whole will come here, but we have a not. So second. Then in the second row, using the De Morgan law of union, so not P here, same. We are going to apply this one to this parenthesis. Not P, not P. This will change to or and not Q. Okay. So in the third one, using double negation law, we have not P. Not P is P, right? So we have not P and P or not Q. Then using distributivity law, we say that not P and P, we are applying this one to here, or not P and Q. Then, because not P and P is always false, this one, we cannot say not P and P. We have not P or P, but we don't have not P and not. So not P and not P is always false. False or not P and not Q. False and something is something always. So we can say not P and not Q false. So we can remove false, then we say not P and not Q, which is the other side, and we proved it. So using the logical equivalences, we could prove that this side equals to this side. So your second assignment is prove this one, about this one, using truth table. So this is the second way. You go for the first way, which was truth table, and let's see that this works or not. All right, so far we studied several topics for the propositional logic. And now we are going to learn predicates and quantifiers. So maybe one question that you have, that why do we need predicates and quantifiers? Because propositional logic cannot adequately express the meaning of all statements in mathematics and especially in natural language. You know, NLP is considered as a branch of AI, and it has a lot of popularity among AI expert, machine learning, deep learning. For example, for recurring neural networks, LSTM, long short-term memories, or transformers, or many things, natural language processing. And the applications are, for example, translators, either text or voice. They use NLP. So very good topic. And this propositional logic has a good role in there. Let's see one example. For example, suppose that we know that every computer connected to university network is functioning properly. So from this statement, how we can use propositional logic to conclude that, for example, math 3 is connected to this one, or how we can conclude that if math 3 is a computer connected to university network, how we can conclude that it's functioning properly. Right? This is how we can do that. For a human being, maybe it's very easy, but how to teach computer to do that is a little bit difficult. Or another example, if x is more than 2, then how we can say that power 2 more than 4. For these things, we use predicates. Predicates in linguistics is considered as how we can, specify what the subject is, or what the subject does, or what the subject tells what is done to that subject. In discrete mathematics, a predicate is a proposition that is a function of one or more variables. For example, we say px, x is even numbers. So even numbers are 2, 3, 5, 7, 11, 13, 17, something, right? So we have x, and predicate said even number, right? Then px is called as propositional function, right? Once a value has been assigned to a variable x, then the statement of px is a proposition. We call it as a proposition. Right? And it has a for example, P1 is considered as a proposition. Then we have quantification or quantifiers. When the variable in a proposition function are assigned values, the result statement becomes a proposition with a certain truth value. The assignment of value to the variables, or we can say subjects, of a statement is called as quantification. We have two important types of quantifiers. One is called as universal quantifier, and the other one is called as existential quantifiers. So this is called as for all. This is called as universal quantifiers. So when we say for all x px, it means x px is applicable to all x, right? All x follows px. And this, we call it that there exist. So in here, for all follows this rule, right? But for here, at least one, there exists at least one. So we call this one as universal quantifier, and this one as existential quantifier. So in this table, we can see for all x px, when it's true, px is true for every x, right? For example, all students at Sejong University are present now, right? So it's applicable to all of them, not even one. But we can say there exists at least one student who is absent because of, for example, visa issues, right? And when it's false, there is an x for which x is not so. If only one fails, then it is wrong, right? When you say for all, it means all. But here, if one is okay, if one member follows, then it's okay. There is one x, at least one, right? And if it's false for all, if px is false for all, then it is wrong. At least there should be one. The universal and existential quantifiers hold their definition in a certain domain. We call it as domain of discourse. Without stating the domain either of these quantifiers, existential and universal, become meaningless. For example, for all a, absolute value of a more than or equal to 0, right? So if it is positive, then more than a. If it is less than this one. So for all, the domain of this one is real number. The universal quantification of P is the statement of Px for all values of x in the domain. When we say all, students of Sejong University means we are talking about students registered at Sejong University, not Seoul National University, not Yonsei. That's why the statement of this proposition is Sejong students, not Yonsei students, right? That's called as domain. For all x px, the universal quantification of px. For all is called as universal quantifier. We read it as, we read this one as for all x px, or you can say, so we call this one for all x px, or you can say for every, right? You can say all of, for each, given any or something, right? An element for which px is false is called as counterexample. Somehow you say contradiction, the opposite side. When the px fails, then they say it as counterexample. Other than two popular quantifiers like universal and existential that we discussed in the previous slides, there can be a number of other quantifiers. You can say like uniqueness quantifier. This is called as uniqueness quantifier, right? This is the notation of uniqueness. And we call it as there exists a unique. We call it as there exists a unique x such that px is true. The quantifiers for all, or you can say universal and existential, they have the highest priority or precedence than all the logical operators that we have so far. For example, if we have this statement for all x px or qx, we should call it as for all x px or qx, right? This is correct. You cannot say for all x px and qx. This is totally different, right? So this has the higher precedence. First we should apply this one, then this one, not these two, then for all, right? That is called as priority or precedence. Look at this example. Every student in your class has taken a course in calculus. It means for all x px, every student, it means all students, something, right? And this px, what is px? Who take a course in calculus. Somehow calculus is prerequisite and all CSE students must pass this course. How we make the negation? It is not the case that every student in your class has a. It means there exists at least one student who did not take any a course in calculus, right? There is at least one negation. We fail it, right? Or you can say there is a student, as I said here, there is a student in your class who has not taken this course. And we show like this: negation of for all x px. Negation of, when negation comes, it means there is one that violates the rule of for all. We can apply the Morgan's law for quantifiers as well. There is no at least one x px equals to for all x not px, at least for one of them. Or you can say there is no for all x px is equal to there exists the x where not px applies. This is the two rules of the Morgan laws that we had already, the Morgan union law and the Morgan intersection law. So when we say there not exists x for px, it means for all x not px. And for every x, px is false when it is true, and for false there is an x for which px is true. Px is true for all this one. And when we say there is no for all x px equals to there exists x where not px, and this is true when there is an x for which px and false for the same. Now we are ready to study the nested quantifiers. So in here, in nested quantifiers, we try to simultaneous quantification of many variables for x and y. Instead of one, we have more than one. More than one variables. For all x and y, x plus y equals 0. We can say every real number has an additive inverse, right? You can call this one as every real number has an additive inverse. What it means? 5 plus minus 5 equals 0. 2 minus 2 plus 2 equals 0, right? This is called as additive inverse. for all x and y, x greater than 0 and y less than 0, then it implies x, y less than 0, right? Where the domain for both variables consists of real numbers, all real numbers. So if we want to translate into English or NLP, natural language processing, for every real number x, and for every real number of y, so real number of x, real number of y, if x is greater than 0 and y is less than 0, then x and y equals to 0. What it means? The product of a positive real number and negative real number is always negative. The product of a positive real number and negative real number is always negative. This is the product, right? So this is called as nested quantifiers. So as the last slide in this lecture, let me give you one summary of the laws we have studied so far. So we have commutative laws, associative laws, distributive laws, identity law, negation law. P O Q equals to Q and P. So it means for and or, for both and or and and, so here is or and here is and. For both or and, commutative laws say you can move the position of two variables. It doesn't matter, both same. In the associative law, it says if you have three variables and you can move these parentheses. It doesn't matter whether you want to calculate first these two together and then this one, or first these two together and this one. The same here, right? So the priority of parentheses can be applied on both the first two or the first last. It doesn't matter. It's called as associative laws. Then we have distributive laws. Distributive law says if we have P and Q or R, if we want to distribute it, just we say P and Q, then another time P and R, and the between will be or, right? And the same here. If you have P outside, Q and R in here, one time we say P or Q and P or R, right? You can apply it outside to the else. We also understood that based on the identity law, P or false is always P and true is always P, right? It's okay. Then we have negation law. We say P and not P is false. P or not P is true. Okay. Then we have idempotent law. We say POP is P and P also P. P and false is false. POT is T, true. Then for absorption law, P and Q or P, no, not the same, is P. P and Q is P, right? Then we had the Morgan laws for union and intersection. Then we had double negation, not P is P. And we had also implication that P on then Q is equal to not P or Q. Okay. So this was the topics that we learned in this lecture. Please study and try to implement in Python. And please feel free to ask me if you have any questions. Thank you.